Before we begin, we have to address the ever important and somewhat controversial topic of what is a fruit. Although this debate will continue to rage on for millennia, the definition we settled with for this video is the developed ovary of a seed plant with its contents and accessory parts as the pea pod, nut, tomato, or pineapple.
The surface of an object reflects and absorbs colors. We only observe the reflected light. The properties of objects determine which wavelengths of light are reflected or absorbed. For example, a ripe banana reflects wavelengths around 570 to 580 nanometers, which corresponds to yellow light. The energy difference between orbitals influences the absorbed wavelength because as the energy jump increases, the wavelength of light absorbed decreases. Ripening is a process due to ethylene that causes the fruit to generally become more palatable, sweeter, redder, or less green, softer, and more acidic. When exposed to oxygen, the colorless gas ethylene reacts to form carbon dioxide and water, which speeds up the ripening process. Artificial ripening agents such as calcium carbide and ethylene gas encapsulated powder are often used. As the ripening process can occur very quickly, sulfur dioxide is often added to preserve the fruit by inhibiting the growth of bacteria, yeast, and molds.
To visualize the ripening process, here we have a time lapse of a strawberry ripening. As you can see, the strawberry starts out green, which is due to the presence of chlorophyll. Over time, the chlorophyll begins to break down and the strawberry changes color. It loses its green color and gains its characteristic red color.
The most commonly seen bell peppers are seen in red, green, and yellow. However, there are also white and lavender colored bell peppers. As all bell peppers start out green, they either stay green or ripen into other colors. Their initial green color is due to its chlorophyll, used in photosynthesis. As they decompose, carotenoid pigments become present, including beta-carotene. In addition, the aroma develops as they ripen, mainly due to bell pepper pyrazine.
Another example of a fruit that changes color during the ripening process is the banana. Once again, we can see the breakdown of chlorophyll playing a central role in this color change from green to yellow. In a banana, chlorophyll is broken down by a series of enzymes. In the first step, magnesium dichylate hydrolyzes the molecule. Also in this step, thiophytanase substitutes a methyl group for the R group. Then thiooxygenase performs essentially a reverse shift-base formation. After this, RCC reductase reduces a carbon-carbon double bond into a single bond. This molecule is either then isomerized or moved to the next set of steps. The resultant molecule from the last slide was a primary fluorescent chlorophyll catabolite. It is further broken down by oxidation, then by esterification, and finally by glucosylation. This resultant catabolite, along with some of the other intermediates, give bananas their yellow color. There are a ton of molecules that give different fruits their different colors. One interesting example is the aubergine, with its deep purple color. This color can be attributed to anthocyanin pigments. One such pigment is nocinin, which is shown here. It comes as a mix of cis and trans isomers around the circled double bond. Another process through which fruits change colors is the rotting or browning process. Many fruits share the chemical process through which this happens, which is called enzymatic browning. In general, fruits have compounds called polyphenols that go through an oxidation reaction, which is catalyzed by the enzyme polyphenol oxidase. The polyphenols are converted to quinones, which go on to react with each other, to ultimately cause the brown discoloration.
To visualize the browning process, here is a strawberry from earlier. Once fully ripened, it starts to go through the enzymatic browning process, which can be seen by the adoption of a darker color. This discoloration can be attributed to the quinones in the strawberry reacting with themselves. Ultimately, these discolorations become more prominent than the main color, and thus the strawberry has gone through its entire color change process.
A specific example of this is the browning of an avocado. Notorious for their quick rotting process, avocados go through the enzymatic browning process fairly quickly. Their polyphenol, catechol, is oxidized into 1,2-benzoquinone. We could take a closer look at this mechanism with this animation. First, both hydroxyl groups are deprotonated by water or some other base. Then the polyphenol oxidase catalyzes an oxidation reaction which causes the electrons on the oxygen to form an extra bond to the carbon on the ring, thus forming the quinone. An important question to ask is how can we change how long this browning process takes? There are a few different ways to accomplish this. One is by adding acid. As can be seen in this time lapse, we've added lemon juice and acid to an avocado while leaving the other one blank. This acid discourages the deprotonation of the polyphenol, which slows down the enzymatic browning process. This ultimately results in the avocado with lemon juice browning at a much slower pace.
Another way to modify the rate of enzymatic browning is the addition of a base. In this time lapse, we have apples with lemon juice and acid, a control, and sodium bicarbonate, a base. The base encourages the deprotonation of the polyphenol, increasing the enzymatic browning process. This ultimately results in the apple with baking soda browning at a far faster rate. A third way to modify the rate of browning is to change the temperature the fruit is stored. In this example, we've cut a banana in half and set one to be placed in the fridge while the other one to be stored at room temperature. We let them sit for a day to track the extent of browning.
The next day.
Temperature can have a profound impact on fruits. In this example, we're comparing bananas stored at room temperature to that stored in the refrigerator. You should never store bananas in the refrigerator, as they are tropical fruits and anything under 58 degrees Fahrenheit can injure them, which is known as under-peel discoloration. It can also lose its nutritional value and aroma. Once you apply heat to vegetables, for example broccoli, the hot water causes pockets of air to expand and escape. This results in a better view of the chlorophyll that gives some vegetables their vibrant green colors. After prolonged heating, the chlorophyll loses magnesium and is displaced by hydrogen from natural acids in the plant, resulting in a duller green. Both fruits and vegetables can come in a wide variety of colors, from red, purplish blue, orange, green, and even whitish brown. Each distinct color has their own set of phytochemicals to help fight diseases. This is where the saying, "eat the rainbow," comes from. The red pigment is from lycopene, which helps reduce the risk of cancer. Purple and blue pigments are from anthocyanin, which acts as an antioxidant to protect cell damage and reduce the risk of cancer, stroke, and heart disease. Orange and yellow pigments are from carotenoids. Green vegetables also contain carotenoids, but they also have indoles and saponins. And finally, brownish white pigments contain allicin, which is known for its antiviral and antibacterial properties.
Do you think any of this even applies to real life?
It has to, right?
job's a joke you broke, your love life's the away. It's like you're always stuck in second gear, when it hasn't been your day, your week, your month, or even your year. But